In this video, we will examine solving problems when an object is connected to another via pulley. As you can see on the picture, one of the objects is on the table and the other is hanging. So for this problem, a 4.4 kilogram mass is connected to an 8 kilogram mass via string over a pulley. The 4.4 kilogram mass is hanging only by the string, and the 8 kilogram mass is being pulled across the tabletop, and the tabletop has a coefficient of friction of 0.250. We're being asked to find the acceleration of the system. The first step to solving these problems is to create free body diagrams based on the forces acting on the objects. So we need to consider what forces are acting on the objects. I'm going to call this object A and this object B so that we don't get them confused. For object A, come over here, and I'm kind of going to do them in a different location just to save my paper. So immediately we've got the force of tension pulling it to the right, and we've got the force of friction pulling it the other way. We've got gravity going straight down, and we've got the normal force going straight up. This is object A. Object B, we've got the force of tension going up and the force of gravity going down. When you have a pulley problem, it is very important that you figure out the direction of motion. So in this case, box A is going to travel this way, and the general direction of motion is like I've drawn in black. We're going to put a positive here because we're going to make that the direction of positive motion. So let's go back over to box A. For box A, the positive direction is to the right. For box B, the positive direction is straight down. So I've written those beside it. This is a good place to stop the video, and if you need to, or think you're able to, try to solve this problem. If you're not quite ready to do this on your own, let's go ahead and set some things up. We need to set up the F-net equations for box A and box B. I'm going to again start with box B. So F-net equals, and because FG is in the positive direction, it's going to be positive. FG minus FT. If I come over to my box A, I've got an X direction and a Y direction. So for my X direction, I'm going to say F-net is equal to FT minus FF. For my Y direction, I'm going to say that F-net is equal to Fn versus Fg. You'll notice I didn't have any indication of what the positive direction is on my drawing. When it's not moving in the positive or negative direction, for, in this case, the Y direction, assume up is positive, down is negative. So assume the traditional orientation. Now, speaking of that, in the Y direction, our F-net is 0. So 0 equals Fn minus Fg. So I'm going to move that Fg over and say Fg is equal to Fn. We've got to be very careful because all of this belongs to box A, and this belongs to box B. We don't want to mess up our masses. If you wanted, you could go ahead and solve for Fn here and get an actual number. Otherwise, we can just hold this to the side and see where it goes. So let's look at the X direction for box A. F-net always equals MA, and M, and it's the A one, times A equals the force of tension minus mu F normal. Remember, that's the equation for the force of friction. Looking over to the right side, you can see you know what the force normal is. So I'm going to go ahead and sub in some more and say mass A times little a, acceleration, is Ft minus mu Fg. I'll sub in a little bit more and say ma times a equals Ft minus mu, and it's Fg is actually mg, and you have to remember which m this is. This is a. And if we wanted to put some numbers to this to kind of stop with the subscripts, we can. So let's do that. Box A is 8 kilograms, so 8A equals force tension minus 0.25 times 8 times 9.8. So let's see, 8A equals Ft minus 19.6. Okay. Well, we have two equations, or rather we have one equation with two unknowns. So let's go see if we can find another equation that we can work with. So let's turn our attention to B's F net equation. So F net is MA, so M, that's specifically B, times A, is equal to Fg, which is mg, mb times g, minus Ft. And you might be a little bit more comfortable if you kind of rearrange this a little bit and put Ft on the left side. Also get some numbers happening, but let's put the numbers in first and see if we can't see something. So the mass of B is 4.4 times the acceleration equals 4.4 times 9.8 minus Ft. And here is the two equations with two unknowns. So this is one equation, this is another equation. I'll go ahead and break this down just a little bit more so that we're not stuck with too much extras. So 43.12 minus Ft. And here you can see why I suggested moving the Ft over. So Ft equals 43.12 minus 4.4a. So I just rearranged the equation. I'm gonna kind of erase a little bit just to make sure we can see. So I've got this equation, and I'm going to sub in my Ft into, well, actually, I'm going to rearrange real quick and say 8a plus 19.6 equals Ft. And then I can just set these two equations equal to each other because they both equal Ft. So 43.12 minus 4.4a equals 8a plus 19.6. And then when you keep going and do more math, your acceleration winds up being 1.90 meters per second squared. But this isn't the only way to approach this problem. Let's look at it more holistically. So starting over, what we could do is look at it as a whole thing that's happening. We would still have the positive direction going around the pulley, but we'd kind of pretend the pulley wasn't even there. That the Fg acting on this and the F friction acting on this box were the things pulling the system forward and holding it back. So let's go from that perspective And let's look at how that would look. We would have an F-net equation that would be equal to the force of gravity acting on box B minus the force of friction acting on box A. This is very much like we did the lab, or like what we did in the lab. So then, and when I put MA here, the question is it an individual mass, A or B, or is it the entire mass? Hopefully you recall from the lab that it is the total mass. So that means we need the total mass here, we need the force of gravity acting on box B, and we need the force of friction acting on box A. So let's kind of break that down. So total mass would be mass of A plus the mass of B times the acceleration is equal to Fg is mg, so mb times g minus mu F normal. And I'm asking you to kind of recall that A had F normal, F gravity, F tension, and F friction, and F normal wound up equaling Fg of A. So F normal was ma times g. So let's plug that in over here. ma plus mb times A equals mb times g minus mu ma times g. So let's see, that's 8 plus 4.4 times A equals 4.4 times 9.8 minus 0.25 times 8 times 9.8. And here again, when you do the math all out, it winds up being 1.90 meters per second squared. Either of these methods will work. Both of these methods are valid. I almost prefer doing the two-step that was before, just so that I can make sure I have all the pieces I need. But it comes down to preference and whether you are confident enough in what's happening and how you've set it all up.